Okay, so we're gonna solve. We're gonna prove that the probability of an empty set is equal to 0. So we start by stating the following, right? That this is gonna be equal to 0. That's gonna be what we're gonna be proving. It's not difficult. We just have to understand what probabilities are. So for example, we have the probability of two sets, right? A union B, right? This will be equal to the probability of A plus the probability of B minus its intersection, right? So knowing this, right, we can write this as asterisk, and then we are going to recall asterisk to say take any set, so the union of these two is going to be A plus, and there's going to be this, minus the intersection of both. Now, we know for a fact that the intersection of anything with an empty set is going to be 0. So the probability of this is 0, basically. Therefore, we can see that, simply put, we know for a fact that PA, right, is going to be equal to PA. Well, basically, also we have to remember, forgot to write this this thing here. We have to remember that any union with an empty set is simply going to be just a set, right? So if we take these two, we can say that PA, right, is equal to PA plus P this minus 0, right? Therefore, we can conclude that P of the empty set is going to be PA minus PA, and that is equal to 0. Therefore, this is equal to 0. And that's how you prove this one. So this time, we're going to be working on how to get or prove monotony. Monotony basically states that whenever we have something being a subset of another set, then this will imply that the probability of the subset is going to be lower or equal to the probability of the upper set or whatever. So let's just write this, and let's say A union B not A. So what does this entail? Simply put, we're just saying that A, right? Imagine a set A is a union. It's plus, right? A and not B. Let's say we have, A and not B, right? So imagine, B and not A. Meaning what we want is this here. So the union of these two is going to give us B, simply put. So the little section that we're missing is going to be given by this union. So, simply put, it's really not that difficult. Now we take the probability of everything. It's going to be equal to the probability of A union B not A. And we know that for a fact, and you see the last video, it is going to be PA plus PB not A minus probability of A intersection of B and not A. Now, B and not A, simply put, let's just see an example here. let's take two little amazing things, A and B, right? So B and not A, right? This will be B and not A, right? So the intersection between A, right, let's just take A, A, intersection between these two is non-existent, it doesn't exist. So this is going to be 0, minus 0. Now this is going to be equal to PA plus PB minus A. Now the important thing here is that we have to understand something. P of A, right, is always going to be lower than something added to it. So it's like saying P of A is lower or equal to P of A plus something, right? So in this case, we're adding this. As we're adding this, this is going to be lower or equal. So we can just declare that this is going to be, right? Meaning that P of A is lower or equal to P of B. And just like that, we have finished the proof. Yeah, it's quite simple once you go step by step. Okay, so we're gonna prove now that the P of AC is equal to 1 minus P of A, right? So how do we declare this? Simply put, we just take that the P of omega, which is a whole sample space, is equal to the union of these two, right? So union of A and AC. We know that a union is given by P A plus P AC minus P, minus P intersection A intersection AC. As we know, there's no intersection, right? So this will simply be P of A plus P of AC. Because there's a complements, there's no intersection, so we can just ignore that. Now, we know for a fact that this equals to 1, right? There's always a possibility for the whole sample space, it's always going to be 1. So we can put this 1 over here, and now we have, right? We have this guy. So now we just have to figure out, and just like that, we have gotten our solution for this. Okay, so this one is a bit more challenging. We have to basically work with this joint sets. So in this case, we have this guy that we just want to prove is that the probability of the union from n equals 1 to infinity of A of n is lower or equal to the sum of the probabilities of A of n. Oh, good. What we do here is we first declare a simple B, right? A B such that A is going to be, simply put, a subset, so to speak. So what we're going to do here is say B of n is going to be A of n, n minus 1, AI. What does this mean? Okay, so B1 is going to be equal to A1, right? There's no A0, so that's it. Then B2 is going to be A2 without A1. And B3, right, is going to be A3 without A1 union A2. And well, B4, of course, is going to be A4 without A1 union up till A3, right? And it continues on to infinity. This will allow for the intersection of these b's to be 0. So if we take the intersection, right, of b of n, sorry, is going to be equal to 0. Simply put, there's the empty set, because there's no intersections, meaning there are disjoint. They are disjointed, or disjoint. I don't know what's the proper term for that. So that's pretty much it. That's the first step we have to take for this to work. Now what we do is understanding the fact that the union of b of I, and well, we can just do n, huh? Yeah, we can just do n, right? The union of all of the bn's is going to be equal to the union of all an's, because at the end of the day, they are the same. So if we take the probability on both sides, it's going to be the same thing, right? So let's just take, just take this and duplicate it, make it a bit smaller. And this guy as well. There we go. That's going to be the same, so to speak. Oh, cool. Now, something that we know, right, is that the union of all of these, if they're disjointed, if we remember what any union is, for example, let's take two sets x union y, is going to be x plus p y minus y x intersection y. Now, if they are disjointed here, x and y are disjoint, then this is equal to 0. Well, this section is equal to 0. Meaning that we will just have this, right? If we compare it in the future. Because these are disjoint, right? In this case, we know that this guy, it's the same property. This guy, the union of bn's, are all disjointed. Their intersection is going to be 0, meaning that this isn't just going to be the sum and 1 of all probability of bn. That's it. Now, we know that bn, right? Bn is a subset A of n. Why do we say that? Because Bn does not include A2 or whatever. It doesn't include anything. Maybe A1 is not disjointed, you know? Maybe A2, for example, could not be disjointed with this one. That could be a case. So in that situation, B2 would be a subset of this. Meaning, per monotony, that we already proved, that this guy is lower than A of n, right? So this applies as well, you know? P of union Bn, right, is equal to lower or equal to probability of union of An, right? Now, as we already stated, well, no, this is not it. Hold on. I did a little mistake here. Let me check it again here. I did a little mistake. So we declared, first of all, that this is this. And then we declared this, right? This is the important part. And then we declare that, yeah, that B is a subset of this, so this will in turn hold, right? And as we know, right, all right, yeah, okay. So as we know, P of these guys are the same, right? So just put it like that. Let's put it in another order so we can understand it better. In this case, we have the following, right? And we know for a fact that this guy is going to be lower than this, right? Lower than, hold on a second. Yeah. So in this case, what we're saying, hold on, let me just delete this. This is the most confusing part. This is where everything comes down. This, right, the probability of Bn is going to be lower or equal to the probability, the sum of probabilities of An. Right? So in this case, what we have to do is simply say, okay, this guy, right, this guy is equal to this. And we know for a fact that this guy is going to be the sum of P of Bn, right? And this is lower than the sum of P of An. Now, so what did we do here? First of all, we created some sets that were disjointed. So meaning these are disjointed from each other, meaning the intersection does not exist, right? Now we know that the union of all of the n's are going to be the same as the an's. So we can declare this as the probabilities are going to be the same. And yeah, simply put, you just use this as a way to show how we get the summation. So this guy is going to be equal to this guy, and the summation is going to be equal to this. Now this doesn't apply to this guy because yeah, it could be disjointed, so to speak. But yeah, we have the same. So now we declare, well, Bn is a subset of An, meaning the probability per monotony is going to be lower or equal to An, right? And we know for a fact that this also applies to the sums, right? So now we just put everything together. We know that this is equal to this, as we already stated, and this one is equal to this, as we already stated. And because these two are linked together in this relationship, we can finish up by saying, right, that P union infinity An as n equals 1 is lower than the probability of n I1 P An. And that's pretty much how we solve this exercise. It's a bit more difficult, but once you get the idea and the intuition behind it, it's not that hard. Okay, so now we're gonna prove the following formula. We want to prove this, right? So you have to understand what any of these means. So first of all, let's just rewrite P of B and what it means, right? P of B would be A intersection B plus P B without A. And you'll see why. So let's do first circles here, 2 circles here. Oops. Just 2 big circles, and then let's do A and B. Okay? And let this guy be the red guy, and this guy be the blue guy. So the red guy is going to give us the intersection. Oops. The intersection, which is given by this. And then we have the blue guy. The blue guy is going to be B without A. So it's going to be this whole section over here. Right? So simply put, that's it. That works. Now, what we want to understand is how can we play with this? Well, we can actually see that P of A, P B without A is equal to P, to PB minus P A without B, intersection B, sorry. So that's what we did. We just reformulated from here, quick and easy. Now what happens next? We want to prove that A union B is, simply put, this guy over here, right? So what we do first is we want to say, okay, what's the union of A and B? The union of A and B means that we cover the whole area, meaning that if we have, again, two big circles, then we would cover everything, right? So including this and that. So we would cover everything. So how can we do this? Well, first of all, let's see what we can do. So we can include A, right? So let's include A. So P of A plus, right? And P of A in this case is gonna cover this whole section, including the intersection that you're gonna see, right? It's gonna cover all this, but we're missing this space, right? So what do? Well, we can say, okay, now I want this guy. I want my PB without A, right? So let's include that, right? Let's just add that, as easy as that, B without A. And we have, there's this whole section covered by this. So we have now this, we know that PB without A is going to be this formula over here. So we can rewrite this, right, as P without P of A, right, plus this. And we just duplicate it, and this is a proof. As you can see, they're the same. So we can call this as proven. And that's pretty much it. So yeah.